Let's start discussing some acid nomenclature. When it comes to naming acids, the first step in the process is to identify the type of acid that we're dealing with. There's two types, binary acids and oxyacids. Binary acids are composed of a proton, and when I say proton, I'm talking about H+. And then something else, an anion that's made directly from an element on the periodic table. So nothing fancy, not a polyatomic ion or anything like that. This is a perfect example here because we see fluorine, and if we were to break this compound into its ions, we would expect H+, and then since fluorine's in group 7, we know it's going to do a -1 charge. So that is a binary acid because it's just two things directly from the periodic table, nothing fancy going on. The binary acids always begin with the prefix of hydro. Then you're going to take the element name and kind of modify it a little bit. Instead of going fluorine or fluoride because it's an anion, you're going to do fluoric. And then just to really emphasize the fact that we're talking about an acid, tack the word acid on the end of its name. So HF is known as hydrofluoric acid. Students often ask me, is this a binary acid? It's got 3 atoms in it, 2 hydrogens and 1 sulfur. Yes, it still qualifies as a binary acid because when we break this compound into its ions, we expect H+ and sulfur, which has a -2 charge because it's in group 6A. So it's really just composed of 2 things. The ratios don't result in just 2 atoms, but that's okay. So we're going to call it hydro. And then sulfur is weird. We're going to keep the sulfur part and tack the ic onto the end. So it's going to be sulfuric acid. In question number 2, we need to go in the opposite direction. We're given the names of acids and we're asked to generate the formulas. Right off the bat, I know that we're dealing with binary acids because of the word hydro out front. Here's how we interpret this. Hydro, an acid, well, that tells me it's H+, crisscrossed with something from the periodic table. And then we have the word iodic in here. Sounds like iodine. Iodine is in group 7 of the periodic table, 7A. So I'm going to give it a -1 charge. So a +1 and a -1. When we crisscross those, that's going to be a 1-to-1 ratio. And the formula for hydroiodic acid then is just going to be HI. Hydro, ding, 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 binary acid, right? And then here we have the word phosphoric. Sounds like phosphorus, and due to its position in the periodic table, I know that as an anion, phosphorus will do a -3 charge. And you're going to crisscross the +1 and the -3. So I'll bring the 3 down. And the formula for hydrophosphoric acid then is just going to be H3P. How will you recognize something as being an oxyacid? So if you have some kind of feeling that you're dealing with an oxyacid, I would take the approach of breaking that compound into its ions. So here, if I'm going to break this down, I have H+, and then I'm looking at this, and because you memorized or really familiarized yourself with that list of polyatomic ions, you see this and you see chromate. A lot of times with the breakdown, students ask me, well, what happened to that 2? that 2 never belonged to hydrogen in the first place. The 2 came from the crisscross. So when they separate, the 2 goes back to the chromate. It goes back to where it came from. Once you break down your compound and you establish that it's an oxyacid because you have a polyatomic ion that contains oxygen and you have H+, that's the acid part, then the key part to remember, the part I write like on top of my test, is 8 goes to ik and 8 goes to os. 8 to ik, 8 to os. So that's your pattern for oxyacids. No hydro involved. Save the hydro for the binary acids. So since this is chromate, I can get rid of the 8 ending and change it to an ik to come up with the name of my acid. So this species is going to be known as chromic acid. Let's break down the next one. So again, it says H3, but hydrogen's in group 1, and it's a solo ion. As a gas, yes, it's H2, but as an ion, it always comes solo. The 3 actually belonged to the phosphate. And this classifies as an oxyacid because it has a polyatomic ion that contains oxygen. Jot down the name of the ion and then establish what pattern it's going to follow. So since it's an 8 ending, I'm going to change it to ik. Always weird with phosphorus and those examples. You'll get the hang of it. This one's going to be phosphoric acid. And this one you'll especially remember once you start doing in-person lab work down the line, because we use phosphoric acid all the time in the lab. So given the names of 2 oxyacids, can we generate the formulas? I know without much thought put into it that they're oxyacids because they're missing the hydro out front. So carbonic. Now this pattern works in both directions. So I got 8 to ik, 8 to os. But if I'm starting with ik, that means that it came from a polyatomic ion with an 8 ending. So if I cross out the ik, I'm thinking about carbonate. This is a super cool acid because it's the acid in soda. Carbonate has the formula CO3 2-, and since it's an acid, I know that it's crisscrossed with H+. So I'm going to redo that crisscross and bring down the 2, giving me a formula of H2CO3 for carbonic acid. Phosphorus. So it sounds different than the previous one. On problem number 3, we had phosphoric. But the os means that it came from an ite polyatomic ion. So I'm thinking about phosphite. Phosphite has the formula PO3 2-, and again with acids we're talking about Arrhenius acid, so we're going to crisscross with H+. So phosphorus acid has the formula H2PO3. So I wanted to share a really cool pattern with you all that may help you remember the names and formulas of the polyatomic ions. I always like to think of the 8 version of a polyatomic ion as being the base polyatomic ion. And so I wrote in chlorate right here next to 8. Now, if you add one more oxygen to that 8 version, and you're going to keep the charge the same on all of the polyatomic ions in the series, then you're going to wind up with perchlorate when you add that extra oxygen. On the opposite end of things, you can start taking away oxygens from your 8 version. And if you take away one oxygen, then chlorate becomes chlorite. And if you take away 2 oxygens from your 8 version or your base version, you're going to add the word hypo in front of the name. So this is hypochlorite. So by memorizing the 8 polyatomic ions and then memorizing this pattern of prefixes and suffixes, you can generate the whole series for any particular polyatomic ion. In terms of the acid formulas, since chlorate and chlorite and hypochlorite, all of the polyatomic ions in this series have a -1 charge. Since the proton, H+, is +1, we know they're going to combine in a 1-to-1 ratio. So here I have HClO, HClO2, HClO3, and HClO4. For the acid names, we're going to build off of the polyatomic names. So since this first polyatomic is hypochlorite, its acid name is hypochlorous acid. Chlorite becomes chlorous acid. Chlorate becomes chloric acid. And perchlorate becomes perchloric acid. So again, taking advantage of the 8 to ic, ite to os pattern there to generate our acid names. Such a cool problem. This is the kind of quiz question or test question that I like because you can't just look up the answers. It really shows me that you understand the pattern, not only for the ions, but also for the acids. So the first piece of information that we're given is the name of this fictitious element, polymerine. And we're told that it's symbolized by a PL and that it's in group 6A. So assuming that it forms a binary acid, let's come up with the formula and name of the binary acid. So we're going to crisscross H plus and PL, and I'm going to give the PL a -2 charge because we were told that it behaves like a group 6A element. So when I crisscross those two things, I get H2PL. And that would be the formula for a binary acid. And since it's a binary acid, we're going to do the same hydroic formula. So I'm going to call this hydro palomoric and then always tack on the word acid at the end. So that's our binary acid. The second piece of information we're given is that the new element forms a polyatomic ion with the formula PlO4 2-, and that it's named palomerate. So because of this 8 ending, I can place this particular polyatomic ion in my ladder of polyatomic ions. So let me start with the formulas. So just plain old 8 would go down here. And then we're going to have a species that has one more oxygen. So we'll do PLO5. And then we're going to have 2 species up here. The first one will be 4, and then I'll take away 1, so I'll do 3 oxygens on that one. And then 1 less oxygen, so now we're down to 2 oxygens on that one. So we got 2, 3, 4, 5. The only thing that's changed as I go through my succession is the number of oxygens. The charge on all the different polyatomic ions has stayed the same. So we were given, and that's how we placed it, we knew PLO4 2- had the name of palomorate. So when the polyatomic ion gains or has an extra oxygen, we're going to put a per in front of its name. So this is going to be perpalomorate. And then, so there's always 2 8s, and the 2 8s have the most oxygens in the sequence. And now we're going to have ite. So this is going to be palomorite or palomorite. And then the one with the least amount of oxygens in the sequence is going to have the prefix hypo in front of it. So hypo palomorite. Such cool stuff, huh? Because I could give you any polyatomic ion and you can complete the sequence. So because the acid names and the acid formulas for those oxyacids are built off of the polyatomic ions, we can predict the formulas and the names of the acids. So on each one of these we have a 2-. So when I think about the crisscross, I'll do an example up here, H plus and PLO2, 2-. I know that the 2 is going to go by the hydrogen. It's going to be a diatomic acid. So just going to grab all those and do the crisscrosses. So here we're looking at H2PLO2. The next one would be H2PLO3. Always diatomic because all of the polyatomic ions had a -2 charge. H2PLO4 and H2PLO5. Almost there. Now we gotta do our I to os, A to ic translation for the acids. So all of this is pretty much going to be the same except for the ending. So it's hypopalomorite. So I'm going to do hypopalomarous acid. So on the next one, it's just palomorite. So we'll just do palomarose acid. So the ites go to os. The last 2 have 8s, so that's going to go to an ic ending. So we're going to do palomaric acid. And then the acid that has the most oxygens will have the per out front. So this will be perpalomaric acid. On letter 6, we're presented with a mixture of binary acids and oxyacids, which we either need to name or come up with formulas for. My first step, my approach when doing this would be to identify each piece of given information as pertaining to either an oxyacid or a binary acid. Remember, you always want to classify before you start naming. So the first example, nitrous acid, this is going to be an oxyacid because it doesn't have the word hydro out front. This formula right here, definitely an oxyacid because we have bromine and oxygen in the formula. Similar rationale over here. We have another oxyacid. And then this last one is going to be the only binary acid of the first group here. And I know that because of the hydro out front. So since it's a binary acid and it's just the crisscross of two things, let me write the formula and get that one out of the way. So we have hydrogen, which has a +1 charge, and then nitric sounds like nitrogen. So I'm going to do N, but since that's in group 5, that's going to have a -3 charge. So the formula for the hydronitric acid will be H3N after I do the crisscross. Alrighty, going back to letter A, nitrous. I know that the ose endings, ite to ose, right? Because oxyacid pattern, ite to ose. So if this has an ose ending, it came from the ite polyatomic ion. So I'll do nitrite, that's what I'm thinking in my head, and nitrite is NO2 minus, so I'm going to crisscross, because it's an acid, I have H plus, I'm going to crisscross H plus and NO2 minus. That gives me a formula of HNO2 for the nitrous acid. Alrighty, continuing on over here, BRO. I don't even know if that's on your list or not. And so if you're at a loss, think of your succession and try to come up with at least one polyatomic ion in that succession. So here with the BRO, I'm thinking of BrO3 minus. And I know the name of that. It's bromate. So since this species here, if I split it up, is H plus and BrO minus, it has 2 less oxygens than bromate. I know that it's going to be hypo prefix and an ite ending. I'm going to use that pattern. So this is hypobromite. Halfway there, we have the name of the polyatomic ion. It's hypobromite. So now I'm thinking about this pattern again, ite to ose. So I'm going to report the name of HBRO as hypobromous acid. Alrighty, next one over here. I don't have a trick for remembering that polyatomic ion, except to just memorize it. But this is permanganate. So when we change it into an acid by combining it with a proton, we're going to take the ate ending and turn it into an ic ending. So this will be permanganic acid. Because ate goes to ic, no hydro, it's not binary. Acetic acid, one of my favorite acids. It's also known as vinegar. So when I think of acetic acid, I get a little bit happy because I think of sandwiches and good deli pickles. I digress. How do we know how to write the formula for acetic acid? Well, because it's an oxyacid and has this ic ending, I know that its polyatomic ion will have an ate ending. So its polyatomic ion will be acetate. Acetate's a little bit confusing because it's presented in a variety of ways. One way, the way I tend to write it is CH3COO minus. I like to write it that way because then when I go to draw the Lewis dot structure, I can really see how things are connected. However, it's oftentimes also written as C2H3O2 minus. Either way is acceptable, and it has a -1 charge. So when it's crisscrossed with the proton, the H+, we know that they're going to combine in a 1-to-1 ratio. Here's where it gets a little bit tricky. There's a bunch of hydrogens in acetic acid. So the formula is CH3COOH, or if you're writing it the other way, C2H3O2H. And this is bothersome to students because usually the hydrogen comes first, and in this case, with acetic acid, we typically tack the hydrogen onto the end. The reason being, there's a lot of hydrogens in the polyatomic ion, and there's 4 hydrogens in the acid form, right? Which acid is actually breaking off? Well, it's going to be the acid that's attached to the oxygen. Hydrogen and carbon share really well. So hydrogens that are attached to carbon atoms directly, like through just one bond, they don't break off. They're not acidic hydrogens. So it's written like this to really emphasize that it's a monoprotic acid. It just produces one H+, and that the hydrogen that's going to break off is attached to the oxygen. Confusing example, again, there's all these little exceptions and quirks with naming, but you'll get used to it and then just like eventually just roll with the punches and kind of be able to interpret weird situations like this. You'll get there. This one, like, yes, this is just a binary acid, right? And it came from H+ and selenium, which is in group 6, so it would do a 2 negative charge. So thinking of selenium and the fact that it's binary, we're going to do hydroselenic acid. Last one is also a little bit weird. We got hydrocyanic acid. So one would think, okay, it's a binary acid, but what element is cyanide, right? And it has the ic ending, so we're like, okay, it's probably gonna either go to back to 8, or since it has the hydro in front, we're thinking cyanide. And cyanide is Cn-. It's one of our polyatomic ions. So hydrocyanic acid, not an oxyacid, and it follows the rules for our binary acids. So we're going to crisscross H+ with cyanide, Cn-, and the formula for hydrocyanic acid will be HCN.